Okay, welcome back to physical chemistry. We're in chapter 18, section 9 now. We talked before about a particle in a one-dimensional box, which is, well, the real world's not one-dimensional, but there are actually some cases where you can pretty well approximate a real system with a one-dimensional box. And we're not going to talk about a two-dimensional box. Instead, we know real-life systems are usually three-dimensional, or should be looked at three-dimensionally if you want to understand them. So we've got a three-dimensional box here. It's in the x dimension this way, and then the y dimension this way, and then the z dimension up this way. So just like we did with the one-dimensional box, inside the box we're saying the potential energy is equal to 0. And then anywhere outside the box in three dimensions, the potential energy is infinite, which is another way of saying that the particle is going to be inside the box at all times, and everywhere inside the box it has the same potential energy, which is 0. So we're going to talk about the dimensions of the box. In x we're going from 0 to a, and then in y we're going from 0 to b, and then in c we're going from 0 to c. And they're not equal to each other. Of course, inequality isn't commutative, but basically a is not equal to b, and b is not equal to c. And of course, a is also not equal to c, even though you can't really conclude that from there. Okay, so the x position of the particle is always going to be greater than or equal to 0 and less than or equal to a. And the y position of the particle is always going to be greater than or equal to 0 and less than or equal to b. And then the z position of the particle is always going to be greater than or equal to 0 and less than or equal to c. Now we're talking about stationary states, of course. So we have the time-independent Schrodinger equation. So this is what it looks like. It's just like we had before, but we've got y and z. So we have our minus h bar squared over 2m. Remember, h bar squared is Planck's constant over 2 pi. And then the m would be the mass of the particle. So all of that times the second derivative of psi with respect to x, plus the second derivative of psi with respect to y, plus the second derivative of psi with respect to z. And then that's equal to E psi. And E is going to be our total energy, which is the same as kinetic energy. Because there can only be two types of energy in a system like this, the kinetic and the potential. And we set the potential 0. So all that we have, the total energy, is equal to the kinetic energy. Now we can write psi as a function of x. So we have an x function, which is a function of the x component of your position. And then your y function, which is a function of your y component position. And then a z function, which is a function of the z component of your position, or the position of the particle, obviously. So we're going to write these as three separate functions. Basically, if you're familiar with probability, you'll know that means we're going to treat x, y, and z as totally independent of each other. So we can just multiply the probabilities. That's what we're going to end up doing. Continue on physical chemistry, chapter 18, section 9. We're talking about a particle in a 3D box. So he said that because the x and y and z dimensions are independent of each other, we can write the psi function as a product of three separate functions. One for x, one for y, and one for z. Now this is what they look like based on what we know from before. So the x component function would be just 2 over a to the 1/2 power, so that's square root, times the sine of nx pi x over a. So remember, a is not acceleration, it's the length of the box in the x dimension. And then just like we had with the one-dimensional box, we have the n that can be 1, 2, 3, 4. We have the same thing for the x component here. Pi is just the number pi. And then x is the particle's position anywhere inside the box. Notice you have the same a in two different places here. So the x component of the energy for the particle in the 3D box is just like you saw for the particle in the one-dimensional box. You have your n, for the x component of n squared, times h squared, Planck's constant squared, divided by 8 times the mass of the particle times the length of the box squared. And then you do the same thing for y, but you have b here, and then you have your y position here, and then the y component of your energy would be the same as before, except you have a different n count for the y, and then of course you have your length in the y component length, so b. And then same for c. You've got your c here and c here instead of your a, and then you have a z, your n count there for z axes, and then your particle's position on the z axis. So your energy in the z-axis will be just the same as before, mh squared over 8m and then the length squared. So multiplying all those together, we get psi. Psi you could write as a function of x, y, and z. So you multiply these and you get 8 over ABC, that's the square root, or 1/2 power. So you have your sine of nx pi x over a, times the next line here, I didn't have room to fit on one line, sine ny pi y over b, and then sine of nz pi z over c. Now energy, of course, is extensive, so you just add it up. The total energy is going to be the x component of the energy, plus the y component of the energy, plus the z component of the energy. So you can factor out the h squared over 8m out of this, and that's what it looks like here. We get the energy is equal to h squared over 8m times the n for the x-axis squared over the length of the box in the x-axis squared, and then same for y and same for z. Now, the ground state then, these n numbers are separate for each dimension, so the ground state would be where all 3 is equal to 1. So when nx equals 1 and ny equals 1 and nz equals 1, that's your ground state. And if they could be higher numbers, 2, 1, 1, or 1, 2, 2, you've got a higher energy system, an excited state. Continuing on physical chemistry, we're at chapter 18, we're starting section 10 now. We're going to talk about degeneracy. So remember in the previous session we talked about a particle in a 3D box, and we explicitly said that A and B and C were different. And the reason is because then it wouldn't experience degeneracy. Now we're going to say, okay, what if A equals B equals C? Well, that would make it a cube. Now remember, a cube has symmetry, and you'll understand in a bit why that's important. And also remember, an atom is very symmetric. You think about a helium atom, basically a perfect sphere, it's got all sorts, you can cut it in half any which way. So it's very symmetric. So in that case, we just replace all the B's and A, or B's and C's with A's, and all the, so we write it like this. Our psi function for a cube only would be 2 over A to the 3/2 power. Remember, because 2 over A times 2 over A times 2 over A to the 1/2, each one of those would be 3/2. So then we have times sine the nx pi x over A, and then sine ny pi y, that's over A now, and then sine n of z pi z over A. So the energy, all those A's are what we had before, the A, B's, and C's, all we have left is A. So we have h squared over 8ma squared times the n of x squared plus the n of y squared plus the n of z squared. Now I already mentioned before in the previous slide that our lowest state, the ground state, would be where nx equals 1 and n of y equals 1 and n of z equals 1. We write that like this, psi of 1, 1, 1. So we x, y, z. 1, x equals 1, y equals 1, z equals 1. We're going to be using this because on the next slide I'm going to explain higher energy states. So for the particle in the 3D box only, at the ground state only, the energy is equal to 3h squared over 8ma squared. Continue on physical chemistry, chapter 18. This is section 10 still. Oops, I spelled next wrong. Okay, so we just talked about the lowest energy level, the ground state for a cubic box, a particle in a 3D box with all 3 sides the same length. Now we're going to talk about the next level up. There's actually 3 different states that have the same energy level. You can have 2, 1, 1, which means that x is 2, y is 1, and z is 1. This is the n count. Or you can have 1, 2, 1, which means that n of x is 1, but n of y is 2, and then n of z is 1. Or you can have psi 1, 1, 2, which means n of x is 1, n of y is 1, n of z is 2. If you do the math and simplify, for all 3 of those levels, all 3 of those states, the energy level is exactly the same. 6h squared over 8ma squared. Guess I could have simplified that to 3/4, but whatever. So these 3 states, psi 1, 1, 2, psi 1, 2, 1, and psi 2, 1, 1, these are different states, but they've got the same energy. So we call these degenerate. Since it's 3-way degenerate, we say it's 3-fold degenerate, or triply degenerate. Degeneracy, if these states are degenerate, that means the states have the same energy. So this is the one I showed you on the previous slide, the ground state. This is what I just showed you on this slide. So the next energy level up also has 3 states. That would be 221, 212, or 122. And then the next state up after that would be 222. So as you can see just by this chart here, this is increasing energy. This is the lowest energy state. These 2 states, they're non-degenerate, but these two energy levels are triply degenerate. Continuing on physical chemistry, chapter 18, we're in section 11 now. We're going to talk about operators. Operators are something you've done before, I'm sure, but you probably never even bothered to call it an operator. So I'm going to give you some examples of operators you've probably already seen before. How about the square root? Now the square root is an operator because you put the square root symbol in front of something and it does something to it. Like in this example, the number 2. You take the square root of 2 and it gives you a number, 1.414, etc. The important thing, remember, this is not multiplication. It's not the square root symbol times 2. It's the square root of 2. This is an operator doing something with this. Likewise, logarithm is an operator. Like if you take the logarithm of 2, I think it's supposed to be natural log actually, but anyway, 0.30 or whatever. So again, it's not log times 2, it's the log of 2. It's doing some sort of operation on this. That's why it's called an operator. Same thing, hopefully you've taken calculus if you watch this. You know what the derivative with respect to x is. This is an operator. Like if you take the derivative with respect to x of x, it's not this times this, it's this of this, and you get 1. Likewise, if you want to square something, you can define this squared as an operator. Or we've been talking about complex conjugates. If you have a complex number or a complex function, you put the star up there, and we said that's the complex conjugate. So we actually said that's an operator, even though we didn't define at the time what an operator is. Now we are going to be using some operators in quantum mechanics, so we're going to have to make sure you can tell them apart from just multiplication or ordinary symbols. So what we do is we put a little hat on top. This hat symbol is called a circumflex. So if we have some operator times A, we're going to symbolize it by writing A hat or A circumflex. And so here we have 2 different, well they might not be different, but we have 2 operators, A and B. So you have A hat and B hat. And what we're saying, we're defining this. Remember 3 lines, that means definition, or always equal. So what we're saying, if we have 2 operators here, A hat plus B hat of f of x, you can distribute. You take the A hat of f of x plus the b hat of f of x. Now don't think of this as the multiplication property of the distributive property of multiplication over addition, because we're not talking about multiplication here. We're talking about operators. So it's just a coincidence that it kind of looks like the distributive property of multiplication over addition. Likewise, you can do an operator of an operator of a function. So let's say we do A of A. We can write that A hat squared of f of x, and then we write that A hat, parentheses, A hat f of x. So this is just order of operation. You're going to do the operator on your function, and then you're going to do it on that result. Now, again, this is for the purpose of order of operations. Let's say you have A hat, B hat, f of x. Well, remember, it's this operator is next to the function, so you have to do this first. So that's why the parentheses goes like this. You do your B hat of f of x, and then you do your A hat of the B hat of f of x. That's the only choice, really. Continuing on physical chemistry, chapter 18, we're in section 11 now. We're talking about operators. So you're probably wondering then, if you have A hat, B hat of f of x, is that the same thing as B hat, A hat of f of x? What you're really asking is that commuting. Does order matter? And the answer is yes, order matters. If they're equal, it really depends on what exactly are A hat and B hat. Some operators will commute, others will not. So you really have to know what the operator means, what it does, how to use it, etc. There's no generic answer. But one thing we do know, if B hat of f of x equals C hat of f of x, this is true if and only if B hat equals C hat. Now, if you're wondering what in the world does quantum mechanics have to do with physical chemistry, it's because each physical quantity has its own operator. So we're going to take the Schrodinger equation and we're going to apply an operator to it to get something useful out of it. So did I say a physical property? Man, I just left out a whole word that time. Anyway, a physical property that we can measure is called an observable. And on the next slide, I'm going to give you some examples of what that means. Continue on physical chemistry, chapter 18, section 11. We're talking about operators still. And we said that any physical property that you can measure is called an observable. So here's a list of some observables. So for position, of course, we have x, y, and z components. So the operator for the x component is just called x hat. The operator for the y component is just called y hat. And the operator for the z component of position is just called z hat. You have the equivalent for momentum. You have p for the x component of momentum. You have p hat of x, and that's just h bar over I times the derivative with respect to x. Now remember, this I is the square root of -1, and of course this here is postulated. I don't know any way you can derive it or if it can be derived at all, but this is what it is. And then you have the equivalent for the y component of momentum. You have p hat for y, that's equal h bar over I times the derivative with respect to y. And then for the z component of momentum, you have just p hat z is equal to h bar over I times the derivative with respect to z. Now energy, E, you might expect it to be called E hat, but normally we write it H hat because it's called the Hamiltonian operator. It's named after the guy who postulated it. So that's why we do it that way. And then time, there is no operator. You may be able to observe it, but it's considered a parameter, which means you're not going to be able to find time from anything else. And then our Hamiltonian, like I said, define energy, it's all this. It's minus h bar squared over 2m, remember m would be the mass of the particle, times the entire quantity, the second derivative with respect to x, plus the second derivative with respect to y, plus the second derivative of z with respect to z, plus the potential energy, which is a function of x, y, z, and t. Remember, this energy can change over time if you have the time-dependent Schrodinger equation. So you need a time-dependent operator, too. So remember, V is potential energy, T is time. Now, one thing I'd like to point out, if you're looking at this here, and you're saying the second derivative of what with respect to x, and the second derivative of what with respect to y, the second derivative of what with respect to z, you're missing the point of operators. This whole thing is not the answer to energy. This is just the operator that you use with the Schrodinger equation to find the energy from your system or your state that is represented by psi. You combine this, and then you get your answer, E, observable. Okay, continue on physical chemistry, chapter 18, section 11. We're talking about operators. We just defined operators. Now we're going to talk about linear operators. We say that B hat is a linear operator if and only if it has these two properties. One, if C is a constant, by the way. So if B hat of C times F is equal to C times B hat of F. In other words, you can pull the constant out. And two, if you have two different functions, F and G, if B hat of F plus G is equal to B hat of F plus B hat of G. If it meets these two criteria, both of them, we say it's a linear operator. Now, there are operators that are linear and there are operators that are not linear. For example, the square root is not a linear operator. The square root of x plus y, it is not the same as the square root of x plus the square root of y. It doesn't meet this second criteria right here. Actually, it doesn't meet the first one either, but one's enough. On the other hand, the derivative with respect to x, that is a linear operator. For example, let's take the derivative of 3x. That is equal to 3 times the derivative with respect to x of x. So it meets the first criteria. And likewise, let's say we have the derivative of this composite function here, x squared plus 10x. That is the same as saying the derivative with respect to x of x squared plus the derivative with respect to x of 10x. So it meets the second criteria. It meets both these criteria, so the first derivative with respect to x is a linear operator. The reason I brought it up It's because we're in quantum mechanics. And in quantum mechanics, all operators are linear. Continuing on physical chemistry, chapter 18, section 11. So we have one operator, pronounced del squared. This is an upside down delta, Greek letter delta squared. And this is called the Laplacian operator. So remember, going from in 3 dimensions, we had a lot of derivatives with respect to x, or second derivative with respect to x, second derivative with respect to y, and second derivative with respect to z. So to simplify that, instead of writing all this over and over, we just define that as equal to del squared. Notice the 3-line equal sign, which means always equal to, or defined as. So our Hamiltonian operator then, by the way, would be equal to minus h bar squared over 2m times del squared plus v. And v here, of course, is the potential energy. So our time-dependent Schrodinger equation would be the Hamiltonian times capital psi is equal to minus h bar over I times the derivative of psi with respect to t. And then, that should be capital psi, shouldn't it? Whoops. Okay, so we have our Hamiltonian operator, our function, derivative of the function, and then h bar over I. So then our time-independent Schrodinger equation, we just put the Hamiltonian of lowercase psi is equal to energy times lowercase psi. Because remember, the potential energy is constant. We don't worry about that. So, or if we can have more than one state, we want to specify a state, then we use lowercase I for that, which is, in this case, is not the square root of -1, even though it's the same I. So we have the Hamiltonian of psi of I equals the energy level of state I times psi of I. Continuing on physical chemistry, chapter 18, section 11. So we showed before that if we have the Hamiltonian of psi of I, that's equal to the energy level times psi of I, where I is the state. So remember, psi, that's our wave function, or the allowed stationary wave function. So obviously we're talking about a stationary state, or a time-independent wave function. So psi of I, that's going to give us our allowed set of energy levels. So we're going to say that psi of I, this is an eigenfunction of the Hamiltonian operator. We're going to talk more about what eigenfunctions and eigenvalues are. So that, if this is the eigenfunction of psi of I, then E of I, the energy level I, is the eigenvalue of psi of I. And then H hat, we said the Hamiltonian, that's the energy operator. This is going to give us the energy of our state. So this formula here, what we have is the energy operator times the wave function, that's equal to the energy times the wave function. When you have it like that, we say this is eigenvalue, eigenfunction. Okay, so since operating on this wave function gives the same wave function back with a constant, we say that this is an eigenfunction of the Hamiltonian. Continuing on physical chemistry, we're in chapter 18, we're still in section 11, talking about eigenfunctions, eigenvalues, and so on, operators. Alright, so let's use an example function. Let's say that our function of x, f of x, is just e to the 2x, and that's equal to psi, because psi is the wave function we do in quantum mechanics. And we're going to use the first derivative with respect to x as our operator. So if you take the first derivative of x, that's our operator, of our function, e to the 2x, you get 2 e to the 2x. Notice the perfect match here. You still have your function, but you've got a constant in front of it, in this case 2. So 2 is our eigenvalue. That's how you find that. So f of x is an eigenfunction because we ended up with the original function and a constant in front of it. Now, average value, if you've taken probability or statistics, you know that's the same thing as expectation value. So let's say you want to know, you have your particle in the 3D box, you should have an average x position, therefore, if you measure it, you would expect the to get that value for x. So let's say we're going to have m. It's just any physical property we might want to measure on our system. So then the average value of this quantity m in quantum mechanics is given by this formula. So we write m in, what do you call these brackets? The greater sign and less than sign. Don't confuse this. I think sometimes they write vectors like this too, but this isn't a vector. This is our average value or expectation value. So it's the integral over all space. So it's the triple integral x to y and z and so on. But we abbreviate it. And instead of writing dx, dy, dz, we just write d tau. That's not a t, that's a tau. And tau means all space. So that's why we can write it over as one integral. It really is a triple integral. So we take our psi star, in this case I'm using capital psi because our time dependent, of m hat times psi. So remember, this star means our complex conjugate. We've talked about that before. Now, this whole formula, this is postulated, not derived. I'm not sure it can be derived or not. It seems like if you've taken statistics, you might be able to try. And then, of course, if we have a real wave function of some sort, or a real function of some sort, then just psi star will be equal to psi. You still write it like this, but putting in the numbers, you just have real numbers. So likewise, for your time independent stationary, your stationary states, you still use the same idea. Your average value for your physical property m is just going to be the integral over all space of psi, lowercase psi star, of m hat, or m hat, and then lowercase psi again. Continue on physical chemistry, chapter 18, section 11. So we already talked about different operators in quantum mechanics. One of them, our observable, was the x component of momentum. And we said that was called p hat of x, or rho hat of x probably, but anyway, that's equal to h bar over I times the first derivative with respect to x. So this is how you would do it with an actual system. You want the average momentum in x, so you just have these brackets, momentum x, and then remember we said in quantum mechanics all operators are linear. So this h bar over I, that's a constant, that comes all the way out to the front just for mathematical convenience. And then we have our triple integral, x, y, z, which one's which doesn't matter. And then you have your psi star, your operator, m hat, or p x hat, whatever. That's the first derivative of x after pulling the constant out front. Because integrals are also, what's it called? Anyway. And then times psi, dx, dy, dz. Continue on physical chemistry, chapter 18. This is the last of section 11. So we're going to talk about non-interacting particles. Now this is not really realistic because remember here in chemistry, the particles we're talking about are actually electrons. Electrons have negative charge, therefore they'll repel each other and other reasons. So again, we're going to start out with this model and then we'll build on it from here. So our psi function is going to be the product of these other functions. The function of 1 for the so this would be for particle 1. So the function for particle 1, which would be the function of the x, y, z in position of particle 1, times the function of particle 2, which would be a function of the x, y, z position of particle 2, and however n many particles we have, then we have the n function of the x, y, z position of particle n. So we just multiply these functions together. Now likewise, energies are extensive, they just add up. So the total energy, again, since they're non-interacting, you just add them up. You have the energy of particle 1 plus the energy of particle 2, etc., all the way to your nth particle. So just like we had before, where the Hamiltonian of F is equal to the energy times F, we do that one particle at a time here. So the Hamiltonian 1 of function for particle 1 is equal to the energy of particle 1 times the function of particle 1. So remember, the F for particle 1, that's our eigenfunction of the Hamiltonian. H hat is our Hamiltonian operator. And then E1, that'd be our eigenvalue for particle 1. That's just like we had before, but we have the same thing for particle 2, 3, 4, etc., all the way to however n many particles we have. So the point is, with non-interacting particles, we have a separate or individual, independent Schrodinger equation for each particle. And if you've ever taken probability, you know that the probability of independent events, you just multiply them together. And remember, our probability is the absolute value of our wave function squared. So the absolute value of our psi squared for the whole system is just equal to the absolute value of the function for particle 1 squared times the absolute value of the function for particle 2 squared times all the way to the absolute value of the function for the nth particle squared. And again, we can only do that because these are independent probabilities. And literally speaking, if you're thinking of a certain spot in space, this is the you might think of it as the location. So the probability of finding all these particles in that certain spot at the same time. Continuing on physical chemistry, we're still in chapter 18. We're doing section 12 now. We're going to be talking about a one-dimensional harmonic oscillator. Now, before we talk about quantum mechanics, we're going to refresh your classical mechanics. Might have been a while since you've had physics. So let's say we have a spring attached to a stationary wall, ceiling, whatever, and we've got a mass on the other end. This spring has a constant k, and our x position is this way, parallel to the movement of the spring. Now, our force on the spring is equal to minus kx. So k, remember, is the spring constant, x is just the position. And we say that's the spring force. This is Hooke's law. Hopefully it sounds familiar, but maybe not. Now, we'll just say in equilibrium, our x position is equal to 0. That's kind of arbitrary, but it makes the math easier, obviously. And then force, it's minus the derivative of v, the potential energy, with respect to x. And that's equal to minus kx. Now remember, the minus sign is because the force is going to go up as displacement goes down. If you don't understand that, you might want to think about it a while. It's kind of important. So rearranging and the minus signs cancel out, we get the differential of the potential energy is equal to the spring constant times the position times the differential of x. We're going to integrate that in a little bit. So remember, x I said is position. It's the amount by which the spring is stretched, which we say is a positive x, or compressed, which is a minus x. Remember, as it's bouncing up and down here, it's going to go up and down from equilibrium. So we're going to have both positive and negative x values. So k, remember, we said is the spring constant. If we're talking about a literal spring, later on we're going to be actually talking about molecular bonds, the stretching within a molecule or between molecules, whatever. So then it's actually a force constant for the bond here. And likewise, for a literal spring, we say it's the stiffness of the spring, or it can actually, at the quantum level, molecular level, be the stiffness, a measure of the stiffness of the bond. So here's that integral I told you we were going to do. The integral of dv, of course, is just v, so that's our potential energy. And the integral of kx dx, k is constant, you pull it out, so you get 1/2 kx squared. And then, of course, you always have an integration constant when you're doing an indefinite integral like that. But we can set potential energy to wherever we want it. So what we're going to do is just say, okay, potential energy, we'll set it so that c equals 0, and that'll simplify here. So the actual formula we have, the potential energy for a spring like this, is 1/2 kx squared. And notice the x squared says parabolic. Okay, so we're in chapter 18, section 12 still. So this is a graph still of the, one-dimensional harmonic oscillator. And we're still talking about classically, the classical picture. So we have a graph of potential energy versus x position here. So we have our equilibrium position here at 0. And it's going to go as far as plus a and minus a. Now classically speaking, this particle cannot go higher than plus a or less than minus a. That's important. We'll come back to that when we talk about quantum mechanics. Now remember, Newton's second law says the force is equal to mass times acceleration, which is mass times the second derivative of x with respect to time. Then from Hooke's law, we know that the force is also equal to minus kx. So taking this part here, we solve for the second derivative of x with respect to time, and we end up with minus k, the spring constant, over the mass m times x position. Now, if you've taken differential equations, you'll notice this is a differential equation, and likewise, if you have linear algebra, you'll notice we have an eigenfunction, eigenvalue problem. So what we need is some sort of function x. Now, you may be wondering why we need a function x, because we say, well, x is our position. Well, yeah, x is our position, but what determines our position? It's got to be a function of something, namely time. So I'm just going to show you the answer here because, well, there's no point in differential equations isn't a prerequisite for this. So this is the answer. Your x position is equal to a times the sine of the square root of k over m times time plus b. So our a and b are integration constants. Of course, this a is the same as that a. It's our maximum amplitude. And then k and m, you already know what those are. K was the spring constant, m is the mass, t is just our time, and then b is another integration constant. Now, it's not shown how you get it from here, but we're going to talk about tau, the period of isolation. Remember this, our particle is going to keep going back and forth, back and forth. So we're going to be describing the time it takes to do that with the letter tau, not to be confused with t, of course. Continuing on physical chemistry, chapter 18, we're in section 12. So here's a graph. Notice I didn't label the axes. So this would be like your position through time, basically. And then this would be your displacement. But the amplitude is kind of arbitrary. It's just to the bottom to the top. So notice it's a sine wave just going up and then back down, coming back to where it started. So from 0 to pi, that's what we call tau. That's one period. We defined on the previous slide what that tau period is. So we have the square root of k over m times tau is equal to 2 pi. So solve for tau, we get 2 pi is equal to the square root of m over k. Now frequency, nu, is just 1 over tau. So that's equal to 1 over 2 pi times the square root of k over m. Now this frequency, this is called the natural frequency. Notice that it doesn't have x in it, so it's independent of x. So whatever your position is along here, the particle's position along here, your frequency is not changing. The frequency of the system stays the same. All it depends on is the stiffness of the spring and the mass of at the end of the spring. Now remember, energy total, that's kinetic energy plus potential energy. Now kinetic energy is 1/2 mv of x squared. This is one-dimensional, remember. And then potential energy, that's just 1/2 kx squared. And of course you add them together, it's extensive. Now we want to substitute for this x using the sine wave we came up with before. A sine square root of k over m t plus b. And then we want to substitute for this vx squared using vx squared is equal to the derivative of x with respect to t squared. Now remember, look at very carefully where the parentheses are. This is the first derivative with respect to t squared. It's not the second derivative. So make sure you pay close attention to that when you're doing a homework problem, or you'll really screw up the math. Okay, continuing on physical chemistry, chapter 18, section 12. So doing those substitutions I talked about on the previous slide, we get the energy total is equal to 1/2 m times k over m times a squared times cosine squared of the square root of k over m times t plus b plus 1/2 times k times a squared times sine squared times the square root of k over m times t plus b. Now we want to factor out this what we can, and notice these m's cancel out. So we get the total energy is equal to 1/2 times ka squared times cosine squared of the square root of k over m times t plus b plus sine squared of the square root of k over m times t plus b. Now hopefully you know sine squared alpha plus cosine squared alpha is equal to 1. Notice these are all the same. It's the same alpha. So we get cosine squared plus cosine squared. All this is equal to 1. So this just simplifies to the total energy of that system, our one-dimensional harmonic oscillator, is equal to 1/2 times k times a squared. That's by classical mechanics. Now we know the energy is greater than or equal to 0. K is obviously going to have to be positive, and a squared is going to be positive. We're talking about real numbers here. And then, of course, x, your x position, it's always going to be greater than or equal to minus a and less than or equal to plus a. Okay, we're continuing on Physical Chemistry, Chapter 18, Section 12. We're going to talk about the one-dimensional oscillator now, but this time we're going to look at it from the view of quantum mechanics. Now remember, there's two parts, kinetic energy and potential energy. The potential energy is going to be the same as quantum mechanics, and it's just based on the position of the particle, and whatever. So potential energy is equal to 1/2 times kx squared. And that's potential energy, we write that as PE or as V. Just depends on who's the teacher, basically. Now, we're going to use the Schrodinger Equation. So we have minus h bar squared over 2m times the derivative of psi with respect to x squared. Oops, should that be second derivative? Uh-oh. Yes, that's supposed to be the second derivative of psi with respect to x squared. Plus 1/2 kx squared psi is equal to energy times psi. Now, this is actually harder to solve than particle in a box. It uses some fancy polynomial called Hermite polynomial. Long story short, the solution you get once you solve that is called the allowed energy levels. So the energy here is going to be V plus 1/2 times h nu. So nu is the frequency of the oscillation we've talked about, just like we did with the classical mechanics. H, of course, is Planck's constant. 1/2 that's constant for real, obviously. And then V is another quantum number. Just like we had particle in the box, we have N, which was 1, 2, 3, 4, etc. This is the vibrational quantum number. It's the same way, it's an integer, but it can be 0. Now the reason it can be 0 is a bit complicated, but basically because that 1/2 in here, so even when V is equal to 0, you still got some energy. So what this shows us is just like particle in a box, the vibrational energy is quantized in quantum mechanics. And like I said, this is not the same idea as particle in a box. N had to be 1, 2, 3, 4, can't be 0, but V can be 0. So make sure you keep that in mind when you're solving homework problems or doing a test problem. Continue on Physical Chemistry, Chapter 18. We're in Section 12 still. So we've got energy levels here. We're going to start at the bottom because that's the ground state. And this is for vibrational energy levels, or the one-dimensional harmonic oscillator in quantum mechanics. So we start at vibrational quantum number V equals 0. So the energy would be 1/2 h nu. Then the next excited state, for V equals 1, the energy would be 3/2 h nu. Oops. And then for the next excited level up, that would be V is equal to 2. So the energy level would be 5/2 h nu. And then the next excited state would be V for the vibrational quantum number equals 3. So energy equals 7/2 h nu. So what that tells us is that the ground state energy, or the 0 point energy, is not equal to 0. So as the temperature of the system goes to 0, the energy, it approaches the ground state, which is not 0. Now the energy levels, 1/2, 3/2, 5/2, 7/2, they're equally spaced, which was different for the one-dimensional harmonic oscillator, or the one-dimensional particle in the box, or the three-dimensional particle in the box. So for V equals 0, this is what the wave function looks like. This is our psi 0. So we have alpha, which is 2 pi frequency times the mass over h bar over 4 to the 1/4 power, 4th root. And that's E, the minus alpha x squared over 2. And then for V equals 1, we have psi 1 is equal to 4 alpha cubed over pi, all that to the 1/4 power, times x, times e to the minus alpha x squared over 2. And then for V equals 2, we have psi 2 is equal to alpha over 4 pi, all that to the 1/4 power, times 2 alpha x squared minus 1 times e to the minus alpha x squared 2. I've never tried to derive these, I don't know where they come from, but you don't have to memorize them, just be ready to use them in a problem. Okay, continue on Physical Chemistry, Chapter 18, Section 12. So we're now talking about the one-dimensional harmonic oscillator from the quantum mechanics point of view. So I showed you the equations for vibrational quantum number equals 0, 1, or 2, or the function psi 0, psi 1, psi 2. So this is what it looks like when you graph it. This would be the probability, or well, whatever the function is, squared. Anyway, so notice that there are no nodes, but it goes off to 0 at plus and minus infinity. And then for v equals 1, it goes through the origin. So there is a node here. And then for v equals 2, it actually goes through 2 nodes. And then for psi 3, there would be 3 nodes. And if you have vibrational quantum number n, it would have n nodes. Now, remember, we're talking about the location of the particle here. And classically, it goes between plus a and minus a. But here, as you can see, it's a curve, and it goes off to infinity. So there actually is, let's say we have minus a here and plus a here. Area under the curve, well, the curve squared actually, it would be probability. As you can see, it's not 0. So there is a probability in quantum mechanics that your particle is going to be way out here or way out here in the regions that we call the classically forbidden region. Continue on physical chemistry, chapter 18. This is the last of section 12. Now, when a particle is in the classically forbidden region, we call that tunneling. Now, if the absolute value of the position of the particle is greater than the absolute value of the amplitude, then obviously the potential energy is greater than the total energy. I can't explain why, but I've been told that doesn't violate the conservation of energy. If you can explain why not, please let me know. Anyway, there is evidence of tunneling though, so this does happen, whether I understand it or not. One is alpha particle tunneling, in other words, radioactive decay. We have the nucleus of an atom. The vertical axis here is energy. So to get out of an atom, it takes about 8 million electron volts. But the alpha particle within the atom, it only has about 4 million electron volts. By classical mechanics, this alpha particle cannot get out of the nucleus of the atom. It does not have enough energy to do so. But as you know, there is such thing as radioactive decay. And the reason it happens is just because there is a probability that it can happen based on the quantum mechanics probability distribution function. Now, another example besides radioactive decay, both types, alpha and beta particle emissions, would be electrons. If you have 2 wires really, really, really close to each other, the electrons can just jump from one wire to the other. So when they're making integrated circuits and other very, very small scale electronics, that can be quite inconvenient for the electrical engineers. And then hydrogen atoms, they also tunnel in nuclear fission. When you get hydrogen atoms close enough together, they actually end up getting together through tunneling.